Okay, this is chromatography. This is a method of separating a mixture of substances. And generally speaking, it is done to find out what's in there rather than a way as preparing a large amount of substance. So it's more analytical rather than preparative. We've got here, we've got a beaker with solvent at the bottom, and we've got a TLC plate in there. Okay, now the TLC plate is it's got silicon dioxide in a very fine powder form sprayed onto the surface of a piece of plastic or a piece of glass, a glass plate. It behaves very much in the same way as paper chromatography. The thing about TLC, it's better than paper chromatography. If you look at the microscopic scale of paper, it's very uneven, lots of fibers, and very random. Whereas if you look at the silicon dioxide, it's a very fine powder, very even, and that means the spots that you get, and if you've probably done paper chromatography, you get big kind of splodges like that. Whereas with thin layer chromatography, you get smaller, more discrete spots if it works well. Okay, so it's better than paper, but it's the same. Basically the same procedure. Okay, so let's say if we are going to use chromatography, we've got a mixture of some amino acids, and so that's going to be on my mixture there. That spot there, that's the mixture, and we've got some standards here. So this one is going to be phenylalanine, which I'll call Phe. Right, that's up there, that substance. And this is aspartic acid, which is there. They're both on the AQA data sheet, those two. Right. Now, if we have a look at these, we can see the R groups are different. Phenylalanine, if you look at this, it's got that. That's going to form van der Waals forces. It's pretty non-polar. Okay, whereas if you look at aspartic acid, the difference in the R group there is you've got a carboxylic acid group on it. So that's going to be, that's probably going to be soluble in polar solvents like water. That is polar. Right, now, if we use, so we're going to put our solvent in here. If we use a non-polar solvent, such as hexane, we're going to use hexane in there. Right, now, first of all, you should make sure that the spots are above the level of the solvent, because otherwise they'll just wash off into the solvent, it won't work. And the solvent's going to start migrating through it will start migrating through the TLC plate, moving up by capillary action. Okay, and eventually when it gets somewhere up there, you can stop it, and then you can see what's happened. Okay, so what would probably happen there is the phenylalanine is non-polar. So that's going to have quite an affinity for the hexane. So that will move up a long way. So you're probably going to get, the spot for phenylalanine will be up here. Whereas the aspartic acid is polar. So that will not dissolve so well in the hexane, and it will have a greater affinity for the stationary phase for the silicon dioxide. So that's probably, we'll move less far, maybe just here. Okay. And then our mixture, well, if we got these spots in the mixture, we've got one there and one there, and say one there. Well, we would know that this blue spot here is, because it moves at the same level as the phenylalanine, that is probably phenylalanine. Let's say this green spot here, that moves at the same rate as the aspartic acid, so that's probably aspartic acid. And then the yellow spot is another substance, and we can't identify what that substance is from this chromatogram. Right, so it's done what it's supposed to do. It has separated a mixture of substances. And how has it done that? Well, it's separated because there's different affinities for the mobile phase, which is the solvent, and the stationary phase, which is, in this case, is the silicon dioxide on the plate. Okay, and whatever you know, that's how chromatography always works. The substances must have different affinities for this mobile phase and for the stationary phase. Right, let's have a think about what would happen in this experiment if we did it, let's say, with, instead of using hexane, let's say we used water. Okay, so we're going to use a polar solvent. Let's not have water, let's have something, let's just have propanone, okay, which is slightly propanone, which is slightly polar because of the carbonyl group on it. Right, so you would get a different result there because they'd have different affinities for the solvent. Right, I would imagine that aspartic acid would have greater affinity for the propanone than would the phenylalanine because it's more polar. Yeah, so that's going to move further up. There, the phenylalanine maybe not move as far because it's less soluble in the propanone because that prefers a more polar solvent because of the big benzene ring group on it. And then our mixture, again, you get one there, and then the unknown, you don't know where that would be. Okay, so if you want to get a good separation, then you need to choose the correct solvent, and that would be done by trial and error. Okay, now that is small scale. Let's have a look at column chromatography now. Okay, right, I'm going to use the same example again, phenylalanine and aspartic acid. We're going to try and separate them. Well, what we have here, we have a glass tube, and in the tube we have an inert material. Okay, it could be silicon dioxide, but it's got to be porous, okay? Because we've got to get liquid to flow through it. So the first thing to do is you're going to lay here's our mixture. I'll do it in green. So you put your mixture of amino acids in there. And then after that, you add on top of it your solvent. And what is going to happen is the solvent is going to move down through the tube. It can either move through gravity, or to make it faster, it can be under pressure. It can be forced through. And what's the solvent going to do? Well, the solvent is going to dissolve the mixture and it's going to carry them through. Let's say that we've got hexane again, which is non-polar. And our phenylalanine is going to be more soluble. Okay, so I think I'll color code them. I'll do the phenylalanine as red, and I'll do the aspartic acid as blue. So first of all, the phenylalanine and the aspartic acid are going to be in roughly the same places, yeah, the top of the column. But as the solvent starts moving through, then because the phenylalanine is more soluble, the phenylalanine is going to start overtaking the aspartic acid, and the aspartic acid will have more of an affinity for the inert, for the stationary phase, and that will still be there. Okay, so roll forward time a little bit. What's going to happen is we're going to have our phenylalanine is all down there, and the aspartic acid is there, and the phenylalanine is going to be the first to elute off the column. Okay, so what will happen is the phenylalanine is going to go into this tube here. Okay, there's all our phenylalanine in there. These tubes I've drawn a little arrow there because they're usually on a little rack and they just keep moving along. Once a minute they'll move along, and you collect a centimeter cubed in there, whatever you want to. So that tube there, what would be in there would just be, that would be empty. Well, it wouldn't be empty, but it'd be just solvent in it. So you'd have all of your phenylalanine in this tube here. And then maybe a few minutes later, when you've got a greater volume of solvent, you've got this tube. By the time this tube here gets up there, you might get all of your aspartic acid collecting in there. So you've separated the two components of the mixture, maybe more components than two, but you'll separate them. So you know if there's anything coming through. You've got a UV sensor here, which will you've got well, the UV is shone through there, and you've got a detector there. So you can tell if it's just solvent coming through or if it's something dissolved in the solvent coming through. And then you can find out what's in each of those tubes. Again, it's the way it works. It is because you have a different affinity. Different affinity for the solvent and for the stationary phase. And that's always the case with chromatography. Right, let's just go back to TLC. There's one thing we need to do is this thing called RF value, which you've actually done at GCSE, but we'll just say, so you've got a couple of spots here. Say this is the start line, and this is where your spot started off. And this is the final position of the solvent. So it's called the solvent front. Okay, and let's say at the end of the experiment, you've got one spot there, one spot there. Okay, now if you want to work out the RF value, and I think the RF value stands for the retardation factor. I think that's what it stands for. Or I think it's sometimes a retention factor. That's just simply equal to the distance of the spot divided by the distance moved by the solvent front. So it's pretty. So obviously, the biggest, the maximum RF value would be 1. Okay, if something moves with the solvent, it never does that, but so it can never be greater than 1. So you would use RF values in TLC, thin layer chromatography. They're not comparable from one chromatogram to another because slight differences in temperature and slight difference in how dense the silica plate is will make a slight difference. So you can't really compare from one to another. You can only compare them on the same chromatogram. You could say if this was a mixture here, right, okay, then those two spots have got identical RF values because they run under identical conditions. Okay, so that is TLC and column chromatography. Very, very similar processes. Don't forget, it's the separation. They separate because of differences in affinity for the solvent, the stationary phase, and the mobile phase.